It's Nupur again. This week I wanted to do something different. So instead of explaining a math concept, I thought I'd demonstrate the solution to a math competition problem, specifically problem 4 of the 2022 AIME 1. So thank you, whoever writes the AIME, for providing this problem. I made sure to give you credit up here. I personally found this problem pretty interesting, and I hope you will too. Here's the problem. There are two numbers w and z. W is equal to the square root of 3 plus I all over 2. Z is equal to -1 plus I times the square root of 3, once again all over 2. We must now find the number of ordered pairs R, S, so that both R and S are positive integers less than or equal to 100, and that I times W to the power R is equal to Z to the power S. When I first looked at this problem, I was thinking, oh geez, taking these numbers to any power, especially if it can get up to 100, sounds like a pig in the poke. You may be thinking that too. But then I realized that these numbers, -1, the square root of 3, and 2, all actually look super familiar. Can you see why they look familiar? If not, maybe it'd help if I rewrote them just a little differently. Does that help? Well, if it doesn't help, I'll just tell you. They remind me of the trigonometric ratios, and for good reason, because surprisingly enough, the sine of pi over 6 radians is equal to, guess what? 1/2. Well, the cos of pi over 6 radians is equal to this 3r, the square root of 3 over 2, which happens to be this other number over here. We find that this sort of logic applies to z as well, only the sine of 2 pi over 3 radians is equal to the square root of 3 over 2. The cos of this same number is equal to -1/2. Now, I think I should give you a little bit of explanation before jumping ahead. There was a very genius mathematician named Euler. Euler is known for tons and tons and tons and tons of things. But one of his most famous contributions is Euler's formula, which is that E being Euler's constant, approximately equal to about 2.7, e to the power I theta is equal to I sine theta plus cos theta. Oh wow, won't you look at that? Both of these numbers are written in this same I sine theta plus cos theta format. So I thought, well, maybe let's try changing these numbers from this format over to this format. This format is also known as polar format. Well, let's do it then. Let's rewrite these numbers. Seeing as we just found out that W is equal to I times sine pi over 6 plus cos pi over 6, W is equal to e to the power I pi over 6. We may apply the same logic to z to get z is equal to e to the power I 2 pi over 3. That's nice. The nice thing about writing them in this polar format is that it becomes much easier to take these numbers up to any power, because now we have to just do some simple multiplication of these exponents. Now, with the numbers in this new format, let's try thinking a little bit about the actual problem itself. So, now that we've written it like this, we can make a few key observations. Number one, w to the power 4 is equal to z. We can verify this pretty easily through simple exponent multiplication. The second and third points are a little more complicated. These points are that w to the power 13 is equal to w, and z to the power 4 is equal to z. Why must this be the case? If you're not familiar with complex numbers, you may be thinking, well, I learned that the only numbers when taken to a positive power that are equal to themselves are 0 and 1. Well, of course that's true for real numbers, but throw that out of the window because now we're dealing with complex numbers. So, the way we can verify this, these 2 points over here, is that we must notice that w to the power 12 equals e to the power I times 2 pi, exponent multiplication, which is equal to I times sine 2 pi plus cos 2 pi. That's another use of Euler's formula. That is equal to 1. And if w to the power 12 is equal to 1, then w to the power 13 must be equal to w. We may apply the same logic to z. Z to the power 3 is equal to 1. Z to the power 4 is equal to z. There is only one last point I must make here, which can be verified in the same way I verified that w to the power 12 is equal to 1. It is that w to the power 3 is equal to I. How is this going to become useful? Well, let's return back to the expression we actually saw in the problem. I times w to the power r is equal to z to the power s. We may substitute this and this into that to get w to the power r plus 3 is equal to w to the power 4s. Of course, r plus 3 is equal to 4s. But wait, we must think a little bit before jumping to this conclusion. There is actually a small issue with this conclusion over here. The issue is simply because of the cyclical nature of taking these numbers up to a power. Suppose we set s is equal to 1. From this equation, we must conclude that r is equal to 1, and more importantly, that's the only value r can have if s is 1. But that is not actually the case, is it? Because w to the power 4 is equal to w to the power 4. That clearly works over here. But w to the power 17 is, but w to the power 16, is also equal to w to the power 4, seeing as w to the power 13 is equal to w. That means that, couldn't we say that r could also equal 13? Couldn't we say that r could also equal 25? See what I mean? This logic over here breaks down because w to the power 4 is not the only power of w that equals w to the power 4. So, let us get rid of this not true equation and think about the problem slightly differently. See, these complex numbers go round and round and round. So to prevent this round and round and round, we can think about 3 cases. These 3 cases have s being less than or equal to 3, and r being less than or equal to 13. These cases that work are 1, 1, 5, 5, 2, and 9, 3. Note that these are like the template cases. This one ends up, when we plug this in over here, ends up in the equation w to the power 4 is equal to w to the power 4. This one, when we plug it in, is going to come up with w to the power 8 is equal to w to the power 8. And this one, w to the power 12 is equal to w to the power 12. If we go beyond that, then we are going to end up with the same round and round problem that I just talked about. So, to end up with w to the power 4 is equal to w to the power 4, the case that we'll call the 1-1 case, because 1, 1. We can note that we may choose 9 numbers for this r. Why? Well, it has a cycle of 12, right? 1, 13, 25, 37, 49, onwards, and note that r must be less than or equal to 100. So that leaves us 9 numbers, including 1. We may use this has a cycle of 3. So we end up with 1, 4, 7, 10. Eventually, we're going to end up with 34 numbers. We may apply the similar logic to these ones. 8 values over here, 33 over here, 8 values over here, 33 over here. Just clarifying one last time, when I describe the cases this way, it might come across as a little misleading. We're really just grouping the cases into 3 categories. The first that ends up with w to the power 4 is equal to w to the power 4. The second that simplifies into w to the power 8 is equal to w to the power 8. The third that simplifies into w to the power 12 is equal to w to the power 12. Anything greater than that 12 is just going to come back around, right? Because w to the power 13 is equal to w. So that's why we group them like this. Now we're just super close to our answer, yay! Now we just need to multiply 34 times 9 for our first case, and 2 times 33 times 8 for our other 2 cases. And that is going to be equal to 834. 834 pairs of R and S that fulfill the conditions of the problem. So there, we solved it, right? So if you have any questions, please comment on my video. I would love to help you. I hope the solution made sense to you and that you had fun watching this video. Thank you, and I'll be back next week. Bye!